Where we left off in the last video, we talked about this interesting phenomenon in waves called Doppler shift, and the fact that as something is moving away from us very, very quickly, its light is stretched longer. So the wavelength becomes more and more like red than it is like blue. And what that means is that the spectral lines that we see are shifted a little bit from where we would expect them to see from the known elements that are in these stars to where we are actually observing them. We're going to now talk about how this predicts some interesting outcomes for our universe. And it comes down to a scientist by the name of Edwin Hubble. You might be aware of this name from the Hubble telescope. And Edwin Hubble's biggest discovery was that the redshift of these stars changes depending on the distance, which means that as a laboratory reference, you would expect to see the redshift or expect to see these lines here. But a nearby star is moving away from us. It's shifted a little bit to the red. Nearby galaxy or distant galaxy, very distant galaxy, we see these lines moving farther and farther towards that red part of the spectrum. What this means is that the farther away it is, the faster it's moving. Now, we're going to talk a little bit about what this means for us, but ultimately, it means not only is like one star moving away from us, all stars are moving away from us, and they're moving away faster if they're farther away. Our universe is expanding. So, the interesting part here is that this expansion looks fairly linear in terms of the distance that it is away versus the velocity that it's moving away. So Edwin Hubble graphed these different standard candles, so known distances away based on how far it's redshifted, and he used that to figure out this graph here, the distance being measured in megaparsecs, so a million parsecs, and the velocity in kilometers per second, which is not a velocity that we hear about very, very often here on Earth. But here we're talking about speeds of like 30,000 kilometers every second. And this relationship is fairly linear. At least what he found was fairly linear. We're going to talk more about that in a little bit. But a linear graph here that goes through zero can be plotted out like this, where the velocity, the y part of this graph, is some constant times d, the x part of this graph, the distance. This constant is the slope. So if we find this slope, we know something about this particular system, and we can calculate the velocity or predict the distance if we know the other one. Now this slope, he gave the name of Hubble's constant, and he found that slope to be about 70 kilometers per second per megaparsec, which means that if it is 1 megaparsec away, it is moving away from us at 70 kilometers a second. And for every megaparsec away that you are farther, you increase that speed by another 70. What's interesting about this is this constant isn't constant. At least it hasn't been proven to be some exact number yet. As our measurements are becoming more advanced and we are able to measure the recession speed of farther and farther away things, this number continually is revised. This roughly 70 came from a study last year in 2019. And there was a study a year or two before that that found it to be different. Like there was one study that was about 68, one study about 73. So we're pretty confident that at least for our local part of the universe that this is pretty close, but it is changing, and we'll find a little bit later on this might not even be linear at all. So this relationship does show up in the IB Physics data booklet. It's right here. Hubble's constant and how it relates to the distance and the velocity that the galaxy or star is moving away. Now, using this Hubble quote-unquote constant is fairly simple. You're given one number and you can find the other. If you want to estimate the distance from the Earth to a galaxy with the recessional velocity of 150 kilometers per second, you can do that. You just look at the redshift, figure out what the speed is, and then plug that in, solving for the distance. So the speed of 150 divided by a Hubble's constant of roughly 70, and you get 2.14 megaparsecs, 2.14 million parsecs. We can do the same thing going the other direction. If a galaxy is 20 megaparsecs from Earth, how fast will it be receding? Go ahead and use 70 kilometers per second per megaparsec as your Hubble's constant, and figure out how fast in kilometers per second that would be. Plugging that in is basically just 70 times 20, so 1400 kilometers per second. This is a really beautifully simplistic explanation of what's going on in our universe. As I mentioned before, there are some complexities there that we'll get into, and some complexities that we don't even understand just yet. But for the most part, this relationship has been a really useful one, not only to understand our universe more, but also to understand more about the distance that things are away from us, because we can use redshift to figure out how fast it's moving, and how fast it's moving to figure out how far away. So if you think about this too long, you're going to start to freak out, because the speed of light is really, it's our time, it's our limit of velocity. Nothing can go faster than the speed of light. But if this truly is linear, then that line is going to keep going. And at some point, it will be going faster than the speed of light. So we need another explanation for this, because the data is showing that it is fairly linear. So if nothing can go faster than the speed of light, but this says that something could be moving away from us faster than the speed of light, what does that mean for our understanding of classical physics? Well, it just means that we need a different explanation of how this is going on. So instead of thinking of these galaxies moving through space, we need to think of it slightly different. In reality, they're not actually moving through space. It's space that is changing. Now, that's kind of a weird concept, but one way that we typically think of our world here on Earth is like if you had an explosion, bits of pieces would be moving away from you in all different directions. They would have some recessional velocity because they are moving through what we know as the space around us. But if you have these galaxies that are at fixed points in space and you stretch space itself, you have a similar thing, that they are going to get farther away from you, but they're not actually moving through that space. So think of, for example, if you had like a rubber band and you were to draw a wave on it, you can stretch that wave, and the wave itself is going to be a longer wavelength and become more and more red. This is another way of explaining redshift, this cosmological redshift. To do so, we can use this relationship here, where Z is the cosmological redshift, R is the current universe size. For our purposes, we're going to use R is equal to 1. And then R naught is the cosmic scale factor. Now that's kind of a weird number. It feels pretty grand to talk about. So think of it as it's basically the size or some fraction of the size of the universe at the time the light was emitted. Which means that most of the light that we see, and we've talked about this before, is million light years away from us, which means that the moment that that light was actually emitted from the star, the universe was younger, and it has stretched throughout space during that time as the universe has expanded. So cosmic scale factor will just be some fraction of what the universe is. It's more useful, I think, easier to see it in an example. So let's plug in some numbers. If the redshift Z is 3, if redshift is 3, what was the scale factor at the time that the light was emitted? We're going to plug in 1 as our current size of the universe. We're going to plug in 3 as the redshift factor, cosmological redshift, and then basically we're just solving for R naught. Multiply or add 1 to both sides, you get 4, and then move things around, you'll end up with R naught, the original size of the universe, is 0.25. What this means for us is that the light had to have been emitted when the universe was a quarter of the size that it is now. So that 0.25, that original size, is basically just giving you the fraction, the ratio of the universe when it was emitted to the universe now. So when we talk about the universe as it's changing, it's useful to think of a physical model. So here, for my physical model, I've just connected some metal washers with some rubber bands. And I want you to think of these washers as different galaxies. So for example, like this washer here could be our Milky Way galaxy. And the rubber bands that are connecting these washers are space itself. And as our universe is expanding, the one great way for us to think of it is that space itself is expanding. So these galaxies are moving farther and farther away from each other, not because they are moving through space, but because space itself is expanding. Now, if you think of yourself being on the Milky Way, and let's say that the end one here is the Milky Way, we can see that all of these galaxies are moving away from the Milky Way. And if you were to watch this first galaxy, this closest one, it doesn't move as fast as its farthest one does. Now that is going to become really important for us to think about as we go to the next step. So imagine a rubber band, and this time you just place dots on the rubber band, something that you can do at home either with washers or with a Sharpie. Now relative to the first dot, which is going to move the fastest as it stretches? So if we watch that stretch out, you'll notice that the farther away it is, the more ground that it's covered in that amount that it's stretched. So even though we're stretching pretty uniformly here, the farther galaxies move away more in the same amount of time than the closer galaxies. What that results in, the outcome, is that these galaxies appear to be moving faster than the nearby. That represents the same thing that we would see in Hubble's law. So from 6 centimeters to 12 centimeters is a bigger change than from 2 centimeters to 4. Both are doubling, but the overall ground that's covered is larger, which means it's moving faster. So in the next lesson, we're going to get more into this idea of expansion because it has been a pretty hot topic for a long time. Talking about, number one, is the universe expanding or not? And then more importantly, how is it expanding? Is it expanding at a constant rate? Is it slowing down? Will it eventually come back and crash in on itself? What is the final outcome of our universe? In our next lesson, we're going to tackle some of those questions and then pull all of these other things back together because really, while it's felt like this unit's been a lot of individual topics, they are all telling the same story. So we're going to tie a thread in our next lesson through all of those different topics and how they are connected.